The fastest object humanity has ever built is screaming through space right now at 430,000 miles an hour, fast enough to cross the United States in 25 seconds. And yet, if you pointed it at the nearest star and waited, it would take 6,600 years to arrive. Not 60, not 600, 6,600. Which means, by every measurement that matters, the stars are permanently out of reach for a single human life. Except they might not be. Because in 1905, a 26-year-old patent clerk in Switzerland, scribbling equations between reviewing electrical gadgets, accidentally found something the universe had been hiding in plain sight. A crack, a loophole, a strange mathematical door that, if you know how to walk through it, could let one human life stretch across entire galaxies in as little as 60 years. Not faster than light, not science fiction. Real physics, tested in laboratories, running quietly inside every GPS satellite floating over your head right now. But the door comes with a condition. One strange, unsettling condition so heavy that most people, when they finally understand it, go very quiet. If you are new here, welcome to Sundown Science. Hit subscribe, pour something warm, and get comfortable. Because tonight, we're going to find out exactly what that condition is, and whether any of us would actually be willing to pay it. Now, settle in, and let's ease into this one slowly. Part 1. The fastest thing humanity has ever built. Picture this with me. You are floating, somehow, just a few hundred meters above the outer atmosphere of the Sunday. The light here is not yellow the way it looks from Earth. It is white, raw, violent, pouring out of a surface that is not really a surface at all, but a seething ocean of plasma the size of 1,000,000. The temperature around you would vaporize steel in under a second. And then, out of the corner of your eye, something moves, not drifts, not glides. It tears past you, a small dart of carbon composite and heat shielding, smaller than a family sedan, and it is gone before your mind can register what it was. That object is the Parker Solar Probe, and at the moment it whips around the Sun at its closest approach, it is moving at approximately 430,000 miles per hour. In metric, that is roughly 192 kilometers every single second. Let that settle for a moment. Every second, every tick of a clock, that probe crosses a distance greater than the length of most countries. It is the fastest human-made object in the history of our species. Nothing we have ever built, from the first gunpowder rockets of ancient China to the most advanced military aircraft ever flown, has moved anywhere close to this velocity. Let me give you a way to feel that speed in your bones, because numbers like 430,000 tend to just slide off the brain without leaving a mark. Imagine you are standing on a beach in San Diego, California, on the western edge of the United States. You look east, toward the Atlantic, and you think about the enormous continent between you and that opposite coast. By car, a trip from San Diego to Jacksonville, Florida, takes roughly 40 hours of pure driving, and most people split that across 4 or 5 days. By commercial airliner, it takes around 5 hours in the air. By the Parker Solar Probe, from the moment it crosses the California coastline until the moment it reaches the Atlantic, it would take about 25 seconds. 25. You could not finish tying your shoes before it had already left the country. Now, hold on to that feeling, because I want to compare this to what a human being has actually experienced. The Apollo astronauts, the men who flew to the moon between 1968 and 1972, were the fastest humans in history. On their return trajectories, as Earth's gravity pulled them back in, they hit peak speeds of around 24,791 miles per hour. That is so fast that a person moving that quickly would cross the Atlantic Ocean in under 10 minutes. It is the kind of speed that rewrote the ceiling of human capability. The Parker Solar Probe is roughly 17 times faster than that. 17. If the Apollo capsule were a bicycle, the Parker probe would be a fighter jet doing a flyby of that bicycle at a velocity the rider could not even perceive. This is not incremental progress. This is a generational leap. This is humanity, within a single lifetime, going from horse-drawn carriages to a machine that can outrun the spin of planets. And here is where the universe reaches down, taps us on the shoulder, and quietly reminds us how small we actually are. Because as impressive as 430,000 miles per hour sounds, the moment you point it at anything outside our own little solar system, the number collapses, it just falls apart. The nearest star system to the Sun is called Proxima Centauri. It is a small, dim, red dwarf star that sits about 4.24 light-years away from us. At the Parker Solar Probe's peak velocity, that trip, in one direction, no stops, no course corrections, no waiting for a launch window, would take approximately 6,600 years. Think about what that means. 6,600 years ago, the pyramids of Giza had not yet been built. Writing had barely been invented. The entire recorded history of the human species, everything we know about who we have been as a civilization, would have to unfold in full, and the probe still would not have arrived. Now bring it down to the scale of a single human life. The average lifespan in a developed country right now is somewhere around 80 years. If the Parker Solar Probe launched on the day you were born and travelled in a perfectly straight line toward Proxima Centauri, how far would it get by the time you died? About 1/20th of a light year, which sounds like something. Until you realize the total distance is 4.24 light years, you would have covered roughly 1/80th of the journey, 1/80th. The rest of the trip, you would leave for 79 more generations of your descendants to complete. And this is at the fastest speed humanity has ever achieved. This is our best, our absolute, no expense spared, cutting-edge engineering best. And against the cosmic backdrop, it is essentially standing still. I want you to sit with the strangeness of this for a moment, because this is the central puzzle that this entire video is going to try to solve. We are not, as a species, slow, not really. We can throw a probe past the sun faster than a rifle bullet, faster than the spin of Earth itself 1,000 times over. Compared to almost any speed our ancestors would have understood, we are gods. But the moment we step off our own little porch and look at the rest of the neighborhood, something inverts. We are not slow compared to horses or trains or jets. We are slow compared to the universe itself. And that is not a sentence I throw around lightly. The universe has a speed at which it operates. It has a natural velocity, a background tempo, and our fastest technology is barely a whisper against it. So the question becomes, if the distance a human can cross in a lifetime is not really a question of how fast we can go with current rockets, what exactly is the limit? What is the wall we keep running into? Is it energy? Is it time? Is it something deeper? Something baked into the rules that govern reality itself? And if there is a wall, the kind of wall that cannot be engineered around no matter how clever we get, is there any door in it? Any loophole? Any crack in the physics that would let one human being cross more than a sliver of the universe before their heart stops beating? Hold that question, because we are about to walk all the way up to that wall together, and then we are going to find the door hidden inside it. And the door will not be where you expect it to be. Part 2, Voyager 1, The Honest Measurement of Humanity. Before we go chasing loopholes and stretching time itself, I want to bring you back down to where we actually live, because the Parker Solar Probe is an outlier. It is a specialized machine built for a very specific, very short mission, and it only achieves those blistering speeds during its closest passes to the sun, when solar gravity is doing most of the heavy lifting. If you want to know how far humanity can actually send something and keep it going in a sustained way through the real, cold, empty dark of interstellar space, you have to look at a different spacecraft entirely. you have to look at Voyager 1. And Voyager 1 is, in my opinion, the most honest measurement we have ever taken of our own reach. Voyager 1 launched on September 5th, 1977, from Cape Canaveral, Florida. Think about that year for a second. The original Star Wars film came out that same summer. Jimmy Carter was in his first year as president. The personal computer barely existed. And while all of that was happening, a small probe, about the size of a subcompact car, carrying a set of instruments that by today's standards would feel almost quaint, lifted off on top of a Titan rocket and began a journey that is still going today. Nearly 50 years later, Voyager 1 has been traveling continuously since the year disco was still popular. It has not stopped. It has not slowed down in any meaningful way. It has just kept going through the outer planets, past Jupiter, past Saturn, and then outward into the black. Today, as I am recording this, Voyager 1 is approximately 15 billion miles from Earth. Say that number out loud. 15 billion. With a B, it is so far away that a radio signal, traveling at the literal speed of light, takes more than 22 hours to reach it, and then another 22 hours to come back. If Mission Control sends a command today, they do not get a confirmation until almost 2 days later. And here is the detail that always stops me cold. Despite that mind-bending distance, despite the fact that Voyager 1 has been flying for longer than most people watching this have been alive, despite the fact that it is the single farthest object humans have ever created, it has still travelled less than 1 light day from Earth. Less than 1. The light from your kitchen lamp, if it could point itself in the right direction, would catch up to Voyager in under a day. In 2012, Voyager 1 crossed what scientists call the heliopause. That is the invisible boundary where the sun's outward-pushing particles finally lose the wrestling match against the pressure of the interstellar medium, the thin soup of gas and particles that fills the space between stars. When Voyager 1 crossed that line, it officially became the first human-made object to enter interstellar space. Think about the weight of that sentence. After all the rockets we have launched, all the satellites we have put in orbit, all the probes we have sent to Mars and Venus and beyond, only one machine has ever actually left the sun's little neighborhood. And it took that machine 35 years of continuous travel to do it. Voyager 1 is currently moving at about 38,000 miles per hour, which is roughly 17 kilometers per second. That is fast. It is significantly faster than the Apollo capsules. But it is also, notice, more than 10 times slower than the Parker Solar Probe at perihelion. And that speed is decaying very slowly as it fights against the faint gravitational pull of the sun that still reaches out even at that distance. The probe is aging. Its plutonium power source, which has been generating electricity through radioactive decay for decades, is running low. Sometime around 2025, engineers expect it to lose the ability to run its scientific instruments. The data will stop flowing. By around 2036, the probe will likely fall completely silent, unable to even signal home. But here is the part that I want you to really feel. After it goes silent, it will not stop. It will just keep going. For tens of thousands of years, this little dark object, no longer talking to anyone, will drift outward through the galaxy, carrying its cargo of quiet. And that cargo is one of the most poetic things our species has ever done. Bolted to the side of Voyager 1 is a golden phonograph record, a 12-inch gold-plated copper disc, along with a stylus and instructions for how to play it. On that record are sounds of Earth, a baby crying, waves on a beach, the song of a humpback whale, greetings in 55 different languages, music from all over the world, including Bach, Chuck Berry, and a haunting Bulgarian folk song called Izlel Yi Delio Haidutin. It was a message, sealed in a bottle and thrown into the largest ocean imaginable. And the people who made it knew, with clear eyes, that the probability of anyone ever finding it is effectively zero. The space between stars is so empty, so preposterously vacant, that Voyager 1 could travel for millions of years without passing anywhere near another object of any significance. In about 40,000 years, Voyager 1 will make its closest approach to another star, a red dwarf called Gliese 445. And when I say closest, I mean it will pass within about 1.5 light years of it, which is not close, which is not even in the same zip code as close. It is a near miss measured by an entire light year and a half. To reach the outer edge of the Oort cloud, the fuzzy spherical shell of icy debris that marks the true edge of our sun's gravitational influence, Voyager 1 will need roughly 30,000 more years of travel. 30,000. That is the time, from the last ice age to the present, repeated, and our most advanced interstellar messenger still has not left its own backyard. So why am I telling you all of this? Why am I spending so much time on this one lonely spacecraft? Because Voyager 1 is the honest number. It is what happens when you strip away the specialized, solar gravity-boosted cheating of the Parker probe and ask, how far can we actually push a machine out into the real, unforgiving distance of interstellar space, using the best technology we have? And the answer, after 5 decades of continuous flight, is less than 1 light day. Remember, Proxima Centauri is over 4 light years away. Voyager 1, in all of its ambition, in all of its decades of effort, in all of its dignified silence still to come, has traveled a fraction of a fraction of a fraction of the distance to even the nearest star. And that is the point. This is the real measurement of our reach, not the peak number on a single exotic mission. This is what we can actually do, sustained, over decades, pointed outward. And it brings us right back to the central puzzle. A human lifetime at Voyager's speed covers almost nothing. A human lifetime at the Parker probe's peak speed still covers almost nothing. No matter which of our best machines you choose, the answer keeps coming back the same. And that sameness is not a coincidence. It is a clue. It is telling us that the real bottleneck is not in the machine. It is in the relationship between velocity, time, and the structure of the cosmos itself. And to see why, we need to talk about what a light year actually means. Because I promise you, whatever picture you have in your head, it is not big enough. Part 3. The scale trap nobody intuitively understands. There is a word that gets thrown around in science documentaries and science fiction movies until it starts to feel familiar, comfortable, almost casual. That word is light year. People say it like they understand it. Oh, this star is 4 light years away. This galaxy is 2 million light years away. And we nod along because the word sounds like a measurement, and we are used to measurements. But I am going to make a claim that might sound strange. No human being truly understands in their gut what a light year is. Not you, not me, not the astronomers who calculate them every day. The number is just too big for the animal machinery of our brains to hold. And that gap between what we can calculate and what we can actually feel is the reason we keep underestimating the problem. So let me try to force you into a real relationship with this number. A light year is the distance that a photon of light travels in 1 Earth year, moving at about 186,000 miles per second, or roughly 300,000 kilometers per second, through a vacuum. In 1 single second, a beam of light can circle the planet Earth about 7.5 times. In 1 minute, it can cross from the Sun to well past the orbit of Mercury. In about 8 minutes, it reaches us here on Earth, which is why when you look up at the Sun, you are actually looking at what the Sun looked like 8 minutes ago. Now take that speed, that unfathomable, universe-limiting speed, and let it run for a full year, non-stop, without ever slowing down. The total distance covered in 12 months is about 9.46 trillion kilometers, or roughly 5.88 trillion miles. That is 1 light year. 1. And it is already a number so big that your brain has almost certainly just stopped trying to picture it. Let me try a comparison that might crack the scale open a little. Voyager 1, our steady, persistent little messenger, has been flying for nearly 47 years. In that time, as we said, it has covered about 15 billion miles, or roughly 20 light hours. In other words, if you asked a beam of light to retrace Voyager 1's entire journey from 1977 to now, it would need about 20 hours to do it. Voyager needed 47 years. Light needs less than a day. The ratio is absurd. It is not a factor of 10. It is not even a factor of 100. Light is moving approximately 20,000 times faster than Voyager 1. And Voyager 1, remember, is still one of the fastest long-duration spacecraft we have ever built. So when you hear that Proxima Centauri is 4 light-years away, what you are really being told is that the light from that star needed 4 years to reach us. And if we wanted to close the gap in the other direction using our current technology, we would need tens of thousands of years. This is the gap. This is the chasm. The speed of light is roughly 150,000 times greater than the speed of most of the machines we send into deep space. 150,000. Write that number down. Tattoo it on the inside of your skull if you have to. Here is a little thought experiment to drive it home. Imagine if Voyager 1 were moving at walking speed, say 3 miles per hour. In that scaled-down universe, how fast would light be moving? Light, at the same scaled ratio, would be moving around 450,000 miles per hour. It would leave the walking Voyager behind so quickly that in the time the probe took 1 step forward, light would have gone somewhere past the moon. And this is the cosmic ratio we are actually working with. Our best technology is the walking pace. Light is the thing that circles the planet multiple times per second, and the universe is measured in units of the second one, not the first. Now, this is the part where most people reach for hope. They think, well, we built cars and then jets and then rockets, and each generation is faster than the last. If you plot human speed over history, it looks like an exponential curve, right? And exponential curves, given enough time, go to infinity. So surely, in another 100 years, or 500, we will have ships moving at a meaningful fraction of light speed. That logic feels good. That logic feels like progress. But it is, unfortunately, wrong. And it is wrong in a very specific and very cruel way that our intuition is not built to handle. Because human intuition evolved for meters, for yards. For the distance between a hunter and a deer, the distance a thrown rock can cover, the distance between a village and a river. Our brains are pattern recognition engines tuned for the scale of the savannah. When we try to apply that same tuning to the scale of the cosmos, we trip over ourselves. We assume that if a little bit of progress got us from horses to jets, then a little more progress will get us from jets to starships. But the universe does not scale linearly. It scales in a way that punishes you more and more severely the farther you try to reach. Let me show you what I mean. Think about this comparison. A jet plane goes about 10 times faster than a car. That feels like a huge leap. A rocket to orbit goes about 50 times faster than a jet. Also a huge leap. The Parker Solar Probe, at peak speed, is about 20 times faster than an orbital rocket. Another huge leap. We are stacking leaps on top of leaps. And yet, even after all of that stacking, we are still only at about 1/600th of the speed of light. To reach even 10% of light speed, a velocity at which interstellar travel starts to become vaguely imaginable, we would need to go another 60 times faster than the Parker Solar Probe. 60. And that is just to get to 10%. To get to 99%, where the real relativistic magic starts to happen, we need another factor of 10 on top of that. We are not talking about incremental improvements. We are talking about rewriting the relationship between energy and motion at a fundamental level. And here is where the history of human speed records starts to tell a worrying story. If you plot the fastest speed ever achieved by any human vehicle, year by year, from the first steam locomotives in the early 1800s all the way to today, you get a curve that climbs and climbs and then, quite visibly, starts to flatten. The biggest leaps happened in the middle of the 20th century, during the space race, when we went from sound barrier breaks to lunar trajectories in about 20 years. Since then, progress has slowed dramatically. The fastest crewed spacecraft ever flown is still the Apollo 10 command module from 1969. That record is more than 50 years old. For uncrewed probes, Parker is impressive, but it only achieves its top speed using the sun's gravity as a slingshot. It is not producing that velocity under its own power. The curve is bending down, not up, and physicists have a very specific, very uncomfortable reason for why this is happening. It turns out that as you approach a significant fraction of light speed, the energy you need to go any faster does not just increase. It does not even just double with each increment. It explodes. It runs away toward infinity. And we have not even gotten close to that wall yet. We are still in the foothills, and already the curve is flattening. So this is the scale trap. This is the thing that almost nobody walking around in daily life truly understands. The gap between where we are and where we would need to be to cross the universe in a lifetime is not a gap that engineering alone can close. We can keep making better engines, better fuels, better designs, and all of it will help at the margins. But it will not, by itself, get us to the stars within a human lifespan. Because the problem is not really about distance. The problem, as I am going to keep coming back to, is about velocity. It is about how much speed you can coax out of a certain amount of energy, and how the universe itself puts a hard ceiling on that trade. Distance is just the stage. Velocity is the actor. And if we want to cross a meaningful piece of that stage before our final act, we are going to have to find a way to manipulate velocity itself in ways that our ancestors could not have imagined. Before we get there, though, I want to deal with the first and most tempting wrong answer, because when people first confront this problem, they almost always jump to the same solution. They say, fine, we just need better rockets. We just need better engines. We just need to pour more resources into propulsion. And I want to show you, gently but firmly, why that is a dead end. Why every single proposal along that line, no matter how exotic, bumps into the same wall that the central thread of this story keeps pointing us toward. Because the real barrier is not in the engine. The real barrier is in the universe itself. And once you see it, you cannot unsee it. Part 4. The first false hope. We just need better rockets. Let us say you are sitting in a room with every rocket engineer on Earth. You have unlimited funding. You have unlimited time. You say to them, I do not care how long it takes. I do not care what you build. I just want the fastest possible ship capable of carrying a human being to another star within a single lifetime. Go. What would they come up with? Well, the first thing they would reach for is something beyond chemical rockets. Because chemical rockets, the kind we use to launch satellites and send people to the space station, are already near their theoretical maximum. They burn fuel like kerosene or liquid hydrogen with oxygen, and the resulting exhaust shoots out the back at around 4.5 kilometers per second. That is the ceiling for chemistry. It is set by the energy stored in the bonds between atoms, and no clever engineering can significantly exceed it. So the engineers would skip past chemistry and start stacking alternatives. First on the list is ion propulsion. You may have heard of it. NASA's Dawn spacecraft, which explored the asteroids Vesta and Ceres, used an ion drive. Instead of burning fuel, an ion engine takes a gas like xenon, strips electrons off the atoms to create charged particles, and then uses electric fields to accelerate those particles out the back at velocities approaching 30 to 50 kilometers per second. That is roughly 10 times more efficient than chemical propulsion. It sounds like a revolution, and in some ways it is. Ion engines can run for years on small amounts of fuel, slowly building up enormous velocities. But here is the catch. The thrust is tiny. We are talking about a force comparable to the weight of a sheet of paper on your hand. It takes weeks of continuous firing just to change a spacecraft's velocity by a noticeable amount. Ion engines are wonderful for robotic probes making long, patient journeys within our solar system. For interstellar travel at meaningful fractions of light speed, they do not even come close. Second on the engineers' list would be nuclear thermal propulsion. In the 1960s, NASA actually built and tested prototypes under a program called NERVA, which stood for Nuclear Engine for Rocket Vehicle Application. The idea is simple in concept. Instead of burning fuel chemically, you use a nuclear reactor to heat hydrogen gas to extremely high temperatures and then shoot it out a nozzle. Because the heat source is so much more intense than any chemical reaction, the exhaust comes out faster, maybe double the speed of a chemical rocket. That is nice, but notice what I just said. Double, not 100 times better, not 1,000 times better. Double. And we are trying to close a gap of 150,000 times to reach the speed of light. A factor of 2 barely registers on that scale. It is the difference between crossing the ocean in a rowboat versus a slightly faster rowboat. Third, there are solar sails. These are enormous, gossamer-thin reflective sheets that catch the pressure of sunlight itself and use it as a gentle, continuous push. Japan's Ikaros mission, launched in 2010, successfully demonstrated this technology in space. The beauty of a solar sail is that it needs no fuel. The drawback is that sunlight is a whisper of a push, and the farther you get from the sun, the weaker that push becomes. You could, in principle, build enormous laser arrays on Earth or in orbit and use them to push a light sail to much higher speeds. And this is exactly what the Breakthrough Starshot project, announced in 2016, proposed to do. The plan was audacious. Build a laser array powerful enough to accelerate a gram-scale probe about the size of a postage stamp with a tiny attached sail up to 20% of the speed of light. At that velocity, the probe could reach Proxima Centauri in about 20 years. For the first time in history, we would be sending something to another star within a single human lifetime. And that is genuinely exciting. But I want you to notice the fine print in what I just said. A gram-scale probe, a postage stamp, not a person, not even a bread box full of equipment, a chip, really. Because the amount of laser energy required to accelerate even a small probe to 20% of light speed is already staggering. Scaling that up to accelerate a human being who masses around 70 kilograms, plus a life support system, plus food, plus water, plus shielding, plus a return trip's worth of fuel, would require energy outputs that exceed the total power consumption of human civilization. Not by a little, by orders of magnitude. The energy requirement does not grow linearly with mass. It does not grow linearly with velocity either. It grows in a way that punishes you brutally the closer you try to get to the speed of light. We will get to exactly why in a little while. For now, just hold the image in your head. Breakthrough Starshot is our best current concept for near light speed travel, and even it cannot carry a human. It cannot even carry a camera of reasonable size, and it has no way to stop when it arrives. The probe would just scream past Proxima Centauri in a few hours of high-speed flyby, taking whatever photos it could, and then continue out into deep space forever. That last point is worth pausing on. Deceleration. When you see spacecraft in science fiction, they accelerate to high speeds and then gently slow down at their destination. In real physics, slowing down is just as hard as speeding up. It requires the same amount of energy in the opposite direction. So if you built a ship that could accelerate a human to even a few % of light speed, you would need a second, equally massive energy source to decelerate them at the other end. Otherwise, Your traveler arrives at their destination moving so fast that they cannot stop, cannot enter orbit, cannot land, cannot do anything but take a very brief look as they blast past. This is one of the unsolved problems of breakthrough starshot. There is, right now, no practical way to slow the probe down when it reaches Proxima. Some have proposed using the target star's own light pressure to brake, but the calculations are marginal at best. For a human mission, the deceleration problem alone would double or triple an already impossible energy budget. And there is more. Beyond these big three categories, there are exotic proposals. Project Orion, dreamed up in the 1950s, proposed propelling a massive spacecraft by detonating small nuclear bombs behind it, literally using the shock waves to push the ship forward. The concept worked mathematically, but no one wanted to detonate thousands of nuclear weapons in near-Earth space, for reasons I hope are obvious. The Daedalus Project, a British Interplanetary Society study from the 1970s, designed a fusion-powered probe that could reach Barnard's star in about 50 years. On paper, impressive. In practice, it required 40,000 metric tons of fuel, made of an isotope of helium that does not really exist in usable quantities on Earth. There have been concepts for antimatter drives, for Bussard ramjets that would scoop up interstellar hydrogen as they flew, for nuclear saltwater rockets and electromagnetic launchers. Every single one of them runs into the same wall, eventually. Either the energy requirements become absurd, or the engineering becomes impossible, or the physics itself turns out to fight you in ways the concept did not anticipate. So here is where this brings us back to the central thread. The question at the heart of this video is not, how fast can we make a rocket? The question is, how much of the universe can a human cross in one lifetime? And what all of these propulsion concepts are quietly, stubbornly telling us is that no matter how clever we are at engineering, no matter how many exotic fuels we find, or how many new physics we dream up, improving rockets does not meaningfully change the answer. It moves the number from 0% of the universe to a tiny fraction of a tiny fraction of a percent. It gets us to our nearest stellar neighbor, maybe, in a human lifetime, at best, in the most optimistic scenarios. It does not get us to meaningful interstellar travel. It does not get us to other galaxies. It does not, even in principle, let us touch more than the tiniest crumb of what is out there. And the reason it cannot is that the problem is not in the machine. The problem is in the equation that governs every possible machine. And that equation, as we are about to see, is not a piece of engineering. It is a mathematical wall carved into the very structure of how propulsion works by the geometry of the universe itself. Once we understand that wall, we will finally understand why no amount of better engineering can solve this problem. And only then will we be ready to look for the door. Part 5. The equation that ends the conversation. In 1897, a Russian schoolteacher named Konstantin Tsiolkovsky, a man who was almost completely deaf and who lived in quiet isolation working through mathematics by himself in a small town, derived an equation that would, in a very real sense, determine the entire future of space exploration. He did not know that at the time. Nobody did. The equation he wrote down looked like a simple piece of arithmetic about rockets. But what it actually described was a ceiling, a mathematical ceiling that no civilization, no matter how advanced, can ever crawl past using ordinary propulsion. And understanding this equation is the single most important step in seeing why we hit a wall when we try to reach the stars. So let me walk you through it, not with heavy notation, but with intuition. The Tsiolkovsky rocket equation says something like this. If you want a rocket to change its velocity by a certain amount, the amount of fuel you need is not proportional to that velocity change. It is exponential in that velocity change. Let me unpack that. A rocket works by throwing mass out its back end, and the faster it can throw that mass, the more push it gets per kilogram of fuel. The speed at which a rocket throws its exhaust is called exhaust velocity, and it is one of the two most important numbers in all of rocketry. The other important number is the mass ratio, which is the ratio of how much the rocket weighs fully fueled compared to how much it weighs after the fuel is burned. The equation says that the velocity change your rocket can achieve is equal to the exhaust velocity times the natural logarithm of the mass ratio. That sounds innocent. It is not. It is a death sentence for interstellar travel, and here is why. Because of the way that logarithm works, every time you want to double the velocity change of your rocket, you have to square the mass ratio. Not double it, square it. Let me give you a concrete example. Suppose you have a chemical rocket with a realistic exhaust velocity, and you want it to reach a velocity of, say, 10 kilometers per second. The equation tells you that your rocket needs to be roughly 90% fuel by mass. In other words, for every 10 kilograms of rocket, 9 kilograms have to be fuel, and only 1 kilogram can be the actual ship, payload, engines, and structure. That is already a brutal ratio. It is why real rockets look like enormous fuel tanks with tiny little capsules bolted on top. Now say you want to go twice as fast, to 20 kilometers per second. You would think you need twice as much fuel. You would be very wrong. You actually need a mass ratio that is squared. So instead of being 90% fuel, your rocket now has to be about 99% fuel. For every 100 kilograms of rocket, 99 kilograms of fuel, and only 1 is the actual ship. And if you want to double the velocity again, to 40 kilometers per second, the mass ratio squares again. You are now at 99.99% fuel, and we are still barely moving compared to interstellar distances. Now, start scaling this toward anything approaching a meaningful fraction of the speed of light. Let us say you want a 1,000 kilogram payload, basically a small crude capsule, and you want to accelerate it to just 1% of the speed of light, which is 3,000 kilometers per second. Run the numbers with chemical propulsion. The mass ratio required is not large. It is not even absurd. It is, and I am not exaggerating here, greater than the mass of the entire observable universe. Let me say that again, because it took me a long time to really believe it the first time I saw it. A chemical rocket capable of pushing a 1,000 kilogram capsule to 1% of the speed of light would need to be more massive than every star, every planet, every grain of dust in the entire visible cosmos, compressed into a single fuel tank. This is not a metaphor. This is not me being dramatic for the camera. This is the actual output of Tsiolkovsky's equation when you plug in real exhaust velocities and real target speeds. The math simply says no. And if you switch to better propulsion, the numbers get slightly less ridiculous, but still remain impossible. A nuclear thermal rocket, with twice the exhaust velocity of a chemical rocket, would only need a mass ratio that is the square root of the chemical rocket's ratio. Sounds good, right? Except the square root of something bigger than the observable universe is still so absurdly large that you would need to harvest multiple galaxies just to fuel your ship. Go to ion propulsion, with exhaust velocities 10 times better than chemical rockets, and the numbers improve, but you still need fuel masses that are millions of times larger than the ship. And the thrust is so low that your rocket would need to run its engines continuously for decades just to reach those velocities, during which time it is still burning through those ridiculous fuel masses. The exponential wall reasserts itself at every turn. What this equation is telling us, in the cleanest, most unforgiving language mathematics has, is that there is a structural limit built into how rockets work. Every time you try to go faster, you need disproportionately more fuel. And the fuel itself has mass, which means you need even more fuel to push that fuel, which means you need even more fuel to push that fuel, and so on. Stacking, which is how real rockets actually work, only delays the collapse. A two-stage rocket helps because you can throw away empty fuel tanks. A three-stage rocket helps more. But staging gives you diminishing returns. You cannot stage your way to the stars. You cannot engineer your way around exponential growth. The wall is there before the first blueprint is drawn. And this is the moment where I want you to feel the weight of what this means. The Tsiolkovsky equation is not a piece of engineering. It is not something that will be solved by better materials, better computers, better manufacturing. It is a mathematical consequence of the basic way that rockets push themselves through space by throwing stuff backwards. Any rocket, anywhere in the universe, ever, run by any civilization, using any fuel, is bound by this same equation. There are no loopholes in it, no clever refinement. It is arithmetic, and arithmetic is not negotiable. So when I said back in part 1 that the barrier is written into the fabric of reality itself, this is part of what I meant. It is not that rockets are bad. It is that the entire concept of a rocket, of propelling yourself by ejecting mass, has a ceiling, and that ceiling is well below the velocities you would need to cross the galaxy in a lifetime. But the Tsiolkovsky equation is not the only wall here. It is the wall that says your fuel has to be finite and your payload has to be reasonable. There is another wall, deeper and more fundamental, that says even the fuel itself has a fundamental limit on how much push it can give you. This is the wall of chemistry. And it is worth a quick walkthrough, because it is the answer to the question you might be asking right now, which is, well, fine, what if we just find better fuel? Part 6. Chemistry as a hard ceiling. Here is a strange thought. Every chemical rocket ever built, from the V-2 missile in World War II to the Saturn V that sent men to the moon, to the Falcon 9 landing itself on barges in the ocean, all of them use essentially the same trick. They take two chemicals, usually a fuel and an oxidizer, combine them in a combustion chamber, and harvest the energy released when chemical bonds rearrange. That energy comes out as hot gas, and the hot gas is what pushes the rocket forward. The faster that hot gas comes out, the more push you get per kilogram of fuel. So the key question, if you are a rocket engineer, is simple. How fast can we make the exhaust? The answer, stubbornly and unavoidably, is about 4.5 kilometers per second for any chemical combination you want to pick. You can use liquid hydrogen and liquid oxygen, the best chemical pairing we know of, and you get about 4.4 kilometers per second. You can use kerosene and oxygen, slightly less. You can use solid fuels, monopropellants, exotic fluorine-based oxidizers, and the numbers wiggle up or down a little, but they cluster around 4 to 5 kilometers per second. None of them get to 10. None of them get to 20. And the reason for this ceiling is not an engineering problem. It is a problem of chemistry itself. When you burn fuel in a rocket, what you are really doing is breaking and reforming the bonds between atoms. Chemical bonds hold a certain amount of energy, and when you rearrange atoms into lower energy configurations, that energy is released as heat. But the energy stored in chemical bonds is, cosmically speaking, tiny. Atoms are held together by the electromagnetic force, which is strong at the scale of individual electrons, but weak compared to the forces inside atomic nuclei. There is a fundamental cap on how much energy you can get from rearranging bonds between atoms, and that cap, when translated into exhaust velocity, comes out to about 4.5 kilometers per second. Every chemical rocket in the universe, built by any species, at any point in history, is limited by this. It is not about cleverness. It is about which forces you are tapping into. Now, why does this matter for our central question? Because it tells us that no refinement of chemical rockets, no matter how much money or research we throw at them, can ever significantly cross this threshold. You might get to 5 kilometers per second with some exotic combination. You might, in theory, approach 6 or 7 with some hypothetical, ultra-dense, energetic material. But you will not get to 20. You will not get to 50. You will not get to the hundreds of kilometers per second you would need to even start making a dent in interstellar travel. Nuclear thermal, which taps into a different, more powerful force, the strong nuclear force inside atomic nuclei, doubles the exhaust velocity to about 9 kilometers per second. Nuclear fission propulsion concepts push this to maybe 50 kilometers per second. Nuclear fusion, if we could figure out how to do it in a controlled, efficient way in a rocket engine, could reach hundreds of kilometers per second. Antimatter, which converts mass directly into energy at the maximum possible efficiency, could, in principle, approach a significant fraction of light speed in exhaust velocity. But each of these steps requires jumping to a fundamentally different physics, a fundamentally different set of forces, and each step gets harder and more energy intensive to produce. So chemistry is a ceiling, it is a universal ceiling. And this connects directly back to our central thread, because what it tells us is that the velocity you can achieve with any reasonable fuel is strictly limited by which forces in nature you are able to exploit. And the velocities required to cross even a small fraction of the galaxy in a human lifetime are so high that no fuel we can realistically harvest and store in any reasonable quantity can reach them. Every alien civilization out there, no matter how advanced, if they are using chemistry, runs into the same 4.5 kilometer per second wall. If they are using fission, the same 50 kilometer per second wall. Physics does not play favorites. So the answer cannot simply be better fuel. The fuel itself is constrained by the rules of the game, and those rules keep telling us the same thing over and over again. Lifetime travel is not about the ship. It is about something deeper. Part 7. The Graveyard of Almost Solutions. Now I want to take you on a quick tour of what I think of as the graveyard. The graveyard of almost solutions. The cemetery where brilliant ideas from some of the smartest humans who ever lived come to be quietly buried under the weight of harder numbers. Because the history of interstellar travel concepts is not empty, it is actually crowded with elegant, creative, genuinely inspired proposals, each of which almost worked, each of which got tantalizingly close before something in the physics pulled it apart. And walking through this graveyard together is important, because it will convince you that this is not a story of insufficient imagination. Smart people have been trying for over a century, and the patterns of failure are instructive. We already mentioned ion propulsion, which has the efficiency but not the thrust. A tiny force applied over years gets you high speeds eventually, but not the tens of thousands of kilometers per second you would need, and not with a meaningful payload. We mentioned nuclear thermal, which doubles the exhaust of chemical rockets but is still thousands of times too slow for interstellar travel. We mentioned gravity assists, those clever slingshot maneuvers where you use a planet's own motion around the sun to pick up velocity for free. Voyager 1 used gravity assists. Parker Solar Probe uses them. But gravity assists are limited by the velocity of the planets themselves. The fastest planet in our solar system is Mercury, orbiting at about 47 kilometers per second. You cannot get more speed from a slingshot than is available in the slingshot itself. And once you leave the solar system, there are no more slingshots to use. Then there is one of the most romantic failures in all of science, the Bussard ramjet. In 1960, physicist Robert W. Bussard proposed that a spaceship could, in principle, scoop up the thin hydrogen gas that fills interstellar space using an enormous electromagnetic funnel, compress that hydrogen, fuse it in a reactor on board, and use the energy to propel itself forward. Because the ship would be collecting its fuel from the space around it as it travelled, it would not need to carry its own fuel supply. In theory, it could accelerate indefinitely, approaching the speed of light over time. The concept was gorgeous. Carl Sagan wrote about it in Wonder. Science fiction authors built whole novels around it. For a while, it looked like humanity's best shot at the stars. And then the calculations caught up to the dream. When physicists actually worked out the details, it turned out that the interstellar medium is so thin and the efficiency of scooping it up so poor that the drag produced by the enormous funnel would actually exceed the thrust produced by the fusion reactor. The ship would, in effect, act more like a giant parachute than a rocket, The faster it went, the more drag it produced, until the two forces cancelled out at a relatively modest fraction of light speed. And that is, assuming you could even build the electromagnetic scoop, which would have to be thousands of kilometers wide and perfectly tuned to the unpredictable density of interstellar hydrogen. The Bussard ramjet, as originally conceived, was quietly retired. It lives on in fiction, but most physicists now regard it as a ghost of an idea rather than a working concept. Other ghosts fill the graveyard. Project Orion, which I mentioned earlier, proposed riding a series of nuclear explosions to the stars. The math said it could work, technically. A ship weighing thousands of tons could be pushed to a few % of light speed by riding a chain of bombs out of the solar system. But the political and environmental consequences were impossible. Detonating nuclear weapons in Earth's atmosphere, or even in near-Earth space, would spread radioactive fallout around the globe, and no treaty regime would allow it. Project Orion was abandoned after the Limited Test Ban Treaty of 1963, and it remains a fascinating what-if. Project Daedalus, a study commissioned by the British Interplanetary Society in the late 1970s, was a more peaceful attempt. It designed a robotic fusion-powered probe that could reach Barnard's star, about 6 light-years away, in about 50 years. The propulsion concept used tiny pellets of deuterium and helium-3, ignited by electron beams in a magnetic confinement system, to produce a stream of fusion exhaust. On paper, the physics worked. In practice, the ship would have weighed 54,000 metric tons, and it would have required several thousand tons of helium-3, an isotope that is essentially absent from Earth and can only be found in useful quantities on places like the Moon or in the atmospheres of gas giants. The engineering was a moonshot built on top of a moonshot. A later refinement, Project Icarus, updated the concept with modern physics, but the fundamental problem remained. You are still burning an absurd amount of exotic fuel to reach just one nearby star one way with no return trip and no crew. And there are others. The Alcubierre warp drive, which proposes using exotic matter with negative energy density to contract space ahead of a ship and expand it behind, gets a lot of press. On paper, it could allow faster-than-light travel without violating relativity, because the ship itself is not really moving through space. The bubble of space around it is moving. The problem is that to generate such a bubble requires negative energy densities that we have no evidence actually exist in the quantities required, and some calculations suggest it would need the mass energy of Jupiter or more, concentrated in an unstable configuration. Every attempt to refine the concept has added new problems faster than it solves old ones. Wormholes, another theoretical shortcut through space-time, require exotic matter to hold them open and would likely be unstable even if we could find or create them. Cryogenic suspension, which is not really propulsion but extends the traveller's effective lifetime, has never been demonstrated for complex organisms and might not be biologically possible for humans at all. Notice what every single one of these failed or unproven concepts has in common. Each of them is trying to solve the same problem, which is how do you get a human being across enormous distances in a reasonable amount of time? And each of them, when examined closely, collapses under the same fundamental constraint. The energy required to push a human-scale mass to a significant fraction of light speed is so enormous that no known fuel, no known engine, no known trick gets you there with anything remotely approaching a realistic payload and mission profile. The rocket equation keeps its grip. Chemistry keeps its sealing. The interstellar medium keeps resisting ramjets. Exotic matter keeps not existing. The graveyard gets fuller. And this brings us right back to the spine of this entire video. If every propulsion method we can imagine, no matter how exotic, fails to carry a human across even a small fraction of a galaxy in a lifetime, then the problem is clearly not propulsion. The problem is the relationship between velocity and the amount of energy the universe will let you have for a given mission. Engineering, as clever as it gets, cannot rewrite that relationship. Something else would have to change. Either the energy budget, which we cannot really expand, or the velocity limit, which appears to be a wall, or, and this is the door we are about to find, the amount of time that passes during the journey itself. Because if you could somehow compress the experience of the trip without breaking any laws of physics, the entire problem changes shape. And that is exactly what a quiet patent clerk named Albert Einstein figured out in 1905. Part 8. The Realization. Let me take stock of where we are. We started with the Parker Solar Probe, the fastest thing humanity has ever built, and we saw that even at its record-shattering velocity, it could not reach the nearest star in 100 human lifetimes. We looked at Voyager 1, our real, long-term interstellar probe, and we saw that after nearly half a century of flight, it has barely crossed 1 light day. We tried to grasp the scale of a light year and realized our brains were not built for it. We imagined better rockets, and everyone we considered, from ion drives to laser-pushed sails, either could not carry a person or could not stop when it arrived, or required energy levels beyond all of human civilization. We confronted the Tsiolkovsky equation and saw that rockets, as a concept, have an exponential wall built into their mathematics. We confronted chemistry and saw that fuel itself has a hard ceiling, and we walked through the graveyard of more exotic ideas, each of which collapsed under its own weight of physics. Every single path has led us to the same place, and that sameness is the clue. Because when every possible answer to a question gives you the same wrong result, it is usually because you are asking the wrong question. We have been asking, how do we build a faster ship? And the universe has been answering, it does not matter how fast your ship is, because the distances are still too great, and the energy required grows exponentially, and there is no amount of engineering that can close the gap. So, let us stop asking that question. Let us ask a different one. What if the bottleneck is not in the distance at all? What if distance, for a traveler, is not a fixed thing, but something that depends on how you move through it? This is the pivot. This is the moment where everything we thought we knew about the structure of reality has to get set down very carefully, picked up again, and rotated 90 degrees in our minds. Because, here is the thing, when we talk about crossing a light year, or 1,000,000 light years, we are assuming that time and distance behave the way they behave when you are standing still, or walking, or driving, or even flying in a jet. We are assuming that an hour is always an hour, and a mile is always a mile, no matter who is measuring them. And that assumption is, at ordinary speeds, essentially correct. It is correct enough that every engineer and navigator and pilot in human history has relied on it without thinking twice. But it is not actually true. It is only approximately true for slow things. When you start to move very fast, approaching the speed of light, time and distance stop behaving the way your intuition says they should. They stretch, they compress. They depend on who is watching. And that is not a metaphor. That is not a mathematical trick. That is the actual structure of the universe, confirmed by a century of experiments baked into the operation of every GPS satellite in orbit around your head right now. So here is the shift. The limit is not distance, because distance itself is not as fixed as we think. The limit is velocity, yes, but velocity does not just determine how fast you cross a fixed distance. Velocity, at extreme values, changes the distance itself from the traveler's perspective, and it changes the time. And this gives us a door, a very narrow, very strange, very costly door. A door that lets us reach, in principle, the entire universe within a single human lifetime. And the person who found that door was a 26-year-old patent clerk who had failed to get an academic job, who was working a desk job examining electrical devices in Bern, Switzerland, and who, in his spare time, was thinking about light. His name was Albert Einstein. The year was 1905. And what he realized that year would turn every problem we have discussed so far inside out. Because the wall is real. The wall is absolute. But hidden inside the wall, carved into its very geometry, is an exit we never knew was there. So let me take you back to a small apartment in Switzerland, to a young man scribbling equations between patent applications, and let me show you how he found it. Part 9, 1905, the question that changed everything. Imagine a summer evening in Bern in 1905. The air is warm, the streets are narrow and cobblestoned. In a modest apartment, a young man with wild dark hair is sitting at a small desk, surrounded by papers. He is 26 years old. He has a degree in physics, but no academic position. He earns his living examining patent applications at the Swiss Federal Patent Office, evaluating devices like electric clocks and telegraph systems. His name is not yet famous. He is, at this point in history, essentially nobody. But between patent reviews, during lunch breaks and evenings, he is quietly rewriting physics. And during this 1 year, which will later be called his miracle year, he will publish 4 scientific papers that will each, individually, earn a lesser man a Nobel Prize. One of those papers, submitted to a German physics journal on June 30th, 1905, is titled, in translation, On the Electrodynamics of Moving Bodies. It is the paper that introduces what we now call special relativity, and it begins with a question so simple that it sounds childish. The question was this: what would it be like to chase a beam of light? Einstein had been thinking about it since he was a teenager. He had imagined himself running alongside a ray of light, moving at the same speed, and he had wondered what the light would look like from that perspective. According to the physics of his time, based on the equations of James Clerk Maxwell, light was an electromagnetic wave moving at a specific speed, about 300,000 kilometers per second. And according to classical Newtonian mechanics, if you chased a wave fast enough, you should be able to catch up to it, match its speed, and see it frozen in place, like a surfer catching a wave and riding along with it. But when Einstein worked through the math, he realized that this picture could not be right. Because if light could appear frozen to a fast-moving observer, it would mean that the laws of physics themselves depended on how fast you were moving. And that seemed absurd to him. The laws of nature, he felt, should be the same for everyone, no matter their state of motion. So he made a leap so radical that it took the rest of the physics community years to even fully accept it. He proposed that the speed of light is not a regular velocity at all. It is not something you can chase and catch. It is a constant, absolute, fixed value, the same for every observer in the universe, no matter how fast they are moving, no matter in which direction. If you are standing still, light moves past you at 300,000 kilometers per second. If you are moving at half the speed of light, light still moves past you at 300,000 kilometers per second. If you are moving at 99% of the speed of light, you would still measure light moving past you at exactly 300,000 kilometers per second. Not less, not more. Always the same. This sounds crazy. It sounds like it violates every piece of common sense we have about how motion works. If 2 cars are moving toward each other, each at 60 miles per hour, we expect them to approach each other at a combined speed of 120 miles per hour. That is how velocities add in the world we grew up in. But if you shoot a beam of light toward an oncoming spaceship moving at half the speed of light, the spaceship does not measure the light coming at 1.5 times the speed of light. It measures the light coming at exactly the speed of light. The relative velocity does not add in the intuitive way. And the consequence of this strange fact, Einstein realized, is that something else has to give. If the speed of light is the same for everyone, then the other quantities we use to describe motion, time and distance must not be the same for everyone. They must adjust. They must stretch and contract in ways that keep the speed of light constant. This is the birth of special relativity. It is the realization that time and space are not separate, absolute backdrops against which motion plays out. They are threads in a single fabric called space-time, and that fabric distorts depending on how you move through it. Clocks on fast-moving spaceships tick slower than clocks on Earth, not by metaphor, but by actual physical measurement. Rulers on fast-moving spaceships are literally shorter along their direction of motion than they would be at rest. And events that happen at the same time for one observer can happen at different times for another observer moving relative to the first. The simultaneity of events, which sounds like something that should be objective and universal, turns out to depend on the observer's state of motion. None of this is mysticism. None of it is philosophical interpretation. It is a direct consequence of the constant speed of light combined with the principle that physics should work the same way for everyone. The mathematical machinery that Einstein used to formalize these ideas had actually been developed a few years earlier by a Dutch physicist named Hendrik Lorentz, who had derived a set of equations known as the Lorentz transformations while trying to explain certain anomalies in electromagnetism. Lorentz had the math, but he did not have the physical interpretation. He thought his equations were a kind of bookkeeping trick to reconcile observations. Einstein took those same equations and said, no, this is not a trick. This is actually how reality works. Time and space are not the absolute containers Newton thought they were. They are flexible, they depend on the observer, and the speed of light is the fixed point around which everything else bends. When Einstein's paper came out, the reception was quiet at first. It was published in a respectable journal, but not widely read. Within a few years, though, as other physicists worked through the implications and began to see that the math matched experiments with surprising accuracy, his idea started to spread. By 1915, when Einstein extended the theory into general relativity and included gravity, he was already becoming a public figure. By the 1920s, after the bending of starlight around the sun was confirmed during a solar eclipse in 1919, he was a global celebrity, and the conceptual foundations he had laid down in that first paper, in that little apartment in Bern, became the bedrock of modern physics. Every piece of technology today that deals with extremely high speeds or extreme precision of timing, from particle accelerators to GPS satellites to nuclear power plants, relies on the equations Einstein wrote in 1905. But here is the part that matters for our story. Buried inside those equations, almost as a side effect of the mathematics, is a quantity that changes everything. A quantity that takes the wall we have been hitting for this entire video and punches a very specific, very beautiful, very terrifying hole in it. That quantity is called the Lorentz factor, usually written with the Greek letter gamma. And gamma is the number that tells you how much time and distance warp for a traveller moving at a given velocity. At ordinary speeds, gamma is essentially 1, meaning nothing much happens. At the speeds of our spacecraft, it is still indistinguishable from 1. But as you approach the speed of light, gamma starts to grow. Slowly at first, then faster, then explosively. And what gamma represents, when you translate it into human terms, is the possibility of a single lifetime stretching far beyond what the universe would otherwise allow. It is the door. It is the loophole. And in the next part, we are going to open it. Part 10. Time dilation, the hidden escape clause. Here is the equation, written out in words instead of symbols. The Lorentz factor, gamma, is equal to 1 divided by the square root of 1 minus the square of your velocity divided by the square of the speed of light. Do not worry if that sentence feels like soup. The only thing you need to understand is what the number does. At a velocity of 0, gamma is exactly 1. Nothing changes. Time flows normally. At 10% of the speed of light, gamma is about 1.005. A tiny, almost imperceptible effect. At 50% of the speed of light, gamma is about 1.15. Still small, but real. At 90% of the speed of light, gamma is about 2.29. Now something interesting is starting to happen. A clock on your ship ticks, for you, at its normal rate. But to an observer on Earth, your clock appears to be ticking less than half as fast. At 99% of the speed of light, gamma is about 7. At 99.9%, it is about 22. At 99.99%, it is about 70. And, as you add more nines, gamma shoots up faster and faster, heading toward infinity as you approach the speed of light itself. This is time dilation. It is not a mathematical illusion. It is not a quirk of perception. It is a real, physical effect that has been measured over and over again in laboratories and on satellites. When you move very fast relative to another observer, time itself runs slower for you from their perspective, and distances contract along your direction of motion. And the effect is not symmetrical, at least not in the way naive intuition might suggest. If you take a journey at high velocity and come back, you really, truly, actually age less than the people who stayed behind. The twins in the famous twin paradox, we will get to them in a bit, are not a thought experiment without consequence. They are a real description of what would happen if you could actually accelerate a human being to significant fractions of the speed of light, and then bring them home. Now let me translate this into the language of our central question. If gamma is 7, that means that 1 year of travel time on the spaceship corresponds to 7 years on Earth. If gamma is 22, 1 year on the ship equals 22 years on Earth. If gamma is 100, 1 year equals 100 years. The effect goes both ways. While people on Earth are experiencing a long interval, the traveller on the ship is experiencing a short one. And from the traveller's own perspective, something strange happens in return. The distance they are travelling through appears to shrink. Length contraction, it is called. A 4 light-year journey to Proxima Centauri, for a traveller moving at high enough velocity, is no longer 4 light-years long. It compresses from the traveller's frame to 1 light-year, or 1/10 of a light-year, or 1/100th. The faster you go, the shorter the distance becomes in your own experience, and the shorter the time required to cross it. This is the loophole. This is the door. Because what this tells us is that there is no fundamental limit on how much distance a single living human being can cross in their own subjective lifetime. None. Zero. You can, in principle, cross the entire visible universe in your own subjective time if you can reach a high enough gamma. The only thing you cannot do is exceed the speed of light. You cannot outrun a photon, but you can, with enough velocity, compress the subjective duration of any journey to as little as you like. The light years ahead of you do not shrink because you are moving faster than light. They shrink because, from your perspective as a high-velocity traveller, space itself is literally less long along your direction of motion. The universe, for you, becomes smaller. Or, equivalently, your lifetime stays the same, but the journey fits inside it. I want you to stop and really feel the shape of this, because it inverts everything we established in the first half of this video. Remember when we were calculating that Proxima Centauri is 6,600 years away at Parker Solar Probe speeds, and that a lifetime covers only 1/80th of that distance? That calculation was correct for Parker Solar Probe speeds. It would still be true if we were stuck at those velocities. But if we could somehow reach a velocity of, say, 99.99% of the speed of light, then, for a traveller at that velocity, the journey to Proxima Centauri would take not 4 years of ship time, but less than a month. Less than a month. A 4 light-year trip compressed into weeks of subjective experience. And the reason this is possible without violating the speed limit of light, is that from the traveler's frame, the distance itself has contracted by a factor of gamma. The laws of physics do not bend. The geometry of space does. Now, you might reasonably ask, wait, if distance contracts in the direction of motion, does that not mean the star I am flying toward is closer to me than it was? Yes, that is exactly what it means. In your frame, as the high-speed traveler, you are not traveling 4 light years at a speed very close to light. You are traveling, from your perspective, a much shorter distance, at a speed very close to light over a much shorter time. The mathematics is consistent. The universe does not break. It just bends in a way that lets a single lifetime become a flexible container, capable of holding journeys that would otherwise require thousands of generations. And here is the deeper beauty of it. Nothing in this loophole violates the rules we established earlier. The speed of light is still the absolute ceiling. You cannot exceed it. The energy required to accelerate a human to gamma 7 or gamma 20 is still absurdly enormous, and we will come back to that in Act 4, because this is not free. But within the rules of the game, the rules that even the most advanced civilization anywhere in the universe must obey, there exists a way for a living being to cross arbitrarily large distances within their own lifetime, without faster-than-light travel, without wormholes, without warp drives, without any exotic physics, just using the basic structure of relativity that a patent clerk figured out in 1905. The universe, it turns out, is not closed to us after all. It is just closed in a way that our slow intuition could not see. And this changes the question we started with. We asked, how much of the universe could a human cross in a single lifetime? And the answer, based on Newtonian physics, based on our current rockets, based on every engineering analysis we have done, was essentially 0, a fraction of a percent. But the real answer, if we allow for relativistic speeds, is radically different. The real answer is that there is no distance in the observable universe that is, in principle, off limits to a sufficiently fast traveler within their own subjective time. The universe, from the traveler's perspective, can be made as small as they need it to be, but there is a cost that is not measured in energy alone, though the energy is staggering. A cost that is measured in something harder, something we have not yet brought into the conversation. Because while the traveler is compressing their own experience, they are leaving behind a world that is not compressing. And that difference, the difference between their clock and the clock of the people they left behind, is the most haunting implication of Einstein's discovery. That is what we are going to explore next. Part 11. The first shock, stars within a lifetime. Let me take the abstract equation we just covered and walk it through some actual destinations. Let me show you what relativistic travel would actually do to the map of the universe if we could achieve the velocities required. Because numbers like gamma 7 and gamma 20 do not really land until you see what they mean in terms of real places in the real cosmos. So let us start small and work outward. Take Vega, a blue-white star about 25 light-years from Earth. It is one of the brightest stars in the northern sky, familiar to anyone who has ever looked up on a summer evening. At ordinary spacecraft speeds, reaching Vega is impossible. Voyager would take over 400,000 years. At Parker Solar Probe speeds, still around 40,000 years. Even at 10% of the speed of light, it would take 250 years of travel, meaning nobody alive at launch would be alive at arrival. But at 99.9% of light speed, with a gamma of about 22, the ship time for the journey contracts to a little over a year, 1 year to Vega. Do you feel that? A destination that is, by every classical measurement, totally unreachable becomes, in principle, a weekend trip by relativistic standards. You could go there, look around, and come back, all within a human career. Now push a little farther. The Pleiades cluster, the beautiful little group of blue stars you can see with the naked eye on a clear winter night, is about 440 light-years away. Classically, absolutely hopeless. Not one single generation of humans could bridge it at current speeds. But at the same 99.9% of light speed, ship time contracts to about 20 years. 20, a young person could leave for the Pleiades at age 20, arrive at age 40, spend a few years exploring, and, in principle, return to Earth at age 60. Except, and this is the catch we will return to, the Earth they came back to would be roughly 900 years older than the one they left. Go farther. The Orion Nebula, that stellar nursery visible just below Orion's belt, is about 1,350 light-years away. Inside that cloud, new stars are forming right now, and you can see them through an amateur telescope, classically unreachable by a factor of tens of thousands. But, at the same relativistic velocity, the journey takes about 60 years of ship time. A lifetime, not a comfortable lifetime, but a lifetime. You could be born on the ship and die at the destination. And now let me push you into territory that I think will genuinely feel like vertigo. The center of our galaxy, the Milky Way, is about 26,000 light-years from Earth. At the supermassive black hole called Sagittarius A star, stars are whipping around so fast that their orbits trace out all kind of cosmic ballet. That region is so far that even thinking about it in classical terms makes you dizzy. At Voyager speeds, it would take 500 million years to reach, longer than complex life has existed on Earth, longer than the dinosaurs. But here is what happens at a gamma of around 500, which corresponds to something like 99.9999% of light speed. Ship time for the journey to the galactic core drops to about 50 years. A single human career could, in principle, carry a person from Earth to the black hole at the center of the galaxy. Read that again. It is not a sentence I expected to ever write. 50 years of subjective experience, and a person could be staring into the throat of a 4 million solar mass black hole. Keep going. The Andromeda Galaxy, the nearest major galaxy to our own, is about 2.5 million light-years away. Most people hear a number like that, and their brain just folds. 2.5 million light-years. Classically, not only is that not reachable in a lifetime, it is not reachable in the entire time the human species has existed, at any speed we can engineer. And yet, at a gamma of about 50,000, which would require a velocity of something like 99.999999999% of the speed of light, the ship time for a journey to Andromeda contracts to about 50 years. 50. A human being, in their own subjective time, could leave the Milky Way entirely, cross the void between galaxies, and arrive in Andromeda within a working career. They could watch another galaxy resolve into individual stars in their windows. They could orbit an alien nucleus. And here is where it gets even more interesting. Most of these scenarios assume a constant velocity, but a real ship would not work that way. A more realistic model is a ship that accelerates at a constant rate, roughly equal to Earth's gravity, which is 1g, for the first half of the journey, and then decelerates at 1g for the second half. This has a lovely side effect. The passengers experience normal gravity the entire trip. No microgravity issues, no bone loss, no muscular atrophy. The acceleration produces a comfortable, Earth-like environment by pushing them into their seats the same way gravity does. Now, the math of constant 1g acceleration under relativistic conditions does something extraordinary. Because the ship keeps accelerating, its gamma keeps growing, and therefore its subjective ship time keeps compressing. Under this model, a constant 1g ship can reach the nearest star in just a few years of ship time. It can reach the galactic center in about 20 years. It can reach Andromeda in about 30 years. And it can cross the observable universe in principle, in about 60 years of ship time. 60 years. Let that sink in. Under the rules of special relativity, plus a comfortable 1g acceleration, a human being could traverse, in their own subjective lifetime, the entire 13.7 billion light-year radius of the visible cosmos. Every galaxy we can see, every star, every distant smudge at the edge of the Hubble Deep Field, all reachable, in principle, within a single life. This is the moment, if this were the whole story, where you would feel only awe. It is the inversion. It is the total flipping of everything we established in Act 1. Remember, in Part 1, we calculated that at Parker Solar Probe speeds, a human covers 1/80th of the distance to Proxima Centauri in a lifetime. 1/80th. The answer to the question, how much of the universe can a human cross in one lifetime, was pretty much nothing. And now we are saying that, at relativistic speeds, the answer is, potentially, all of it. Every reachable point. 100%. Through the exact same physics that earlier said no, by exploiting one small specific feature of that same physics, we have opened the universe from fully closed to fully open. The door is real. It works. It is not fiction. But this is also the moment where a good friend has to stop you at the top of a staircase and point down into the basement. Because this door comes with conditions, 3 of them. 3 conditions that are each, in their own way, more unsettling than anything we have talked about so far. The first is the energy. The energy required to reach these gammas is so enormous that it dwarfs the entire output of human civilization. The second is the nature of the journey itself. At these velocities, the universe you travel through becomes alien, not metaphorically alien, physically, visually, dangerously alien. And the third condition, the one that will stay with you long after you finish this video, is the nature of what you leave behind. Because while your clock is ticking slowly, Earth's clock is not. And every mile you gain in space, you lose in time. That is the part we have to talk about next. Because the most famous thought experiment in all of relativity, the one that makes this concrete, is the story of 2 twins, one who stays, one who goes. And one of them comes back to a world that no longer knows them. Part 12. The twin paradox, where it stops being abstract. Here is the scenario. 2 identical twins, let us call them Anya and Nora. They are 25 years old. They are as similar as 2 people can be. Same DNA, same memories of childhood, same view of the night sky out their bedroom window growing up. One day, they get the extraordinary opportunity to split their lives in an experiment. Anya is going to stay on Earth. She will live her normal life, marry, have children, watch the seasons change, grow older in the regular human way. Nora is going to board a relativistic spaceship and travel to a star about 20 light years away at a velocity of 99.5% of the speed of light, which gives her a gamma of about 10. She will travel there, turn around, and travel back. It sounds straightforward. 2 journeys, each of 20 light years, for a total round-trip distance of 40 light years. From the Earth's perspective, Nora's round trip, measured by Earth-based clocks, takes about 40 years. She left at 25. She comes back at 65. That is what Anya experiences. 40 years pass for her while her sister is gone. She raises children. Those children grow up. Some of them have grandchildren. The world changes, politically, technologically, socially. 40 years is a long time. When Nora's ship finally returns and lands, Anya is an old woman, 65 years old, her hair grey, her face carrying 4 decades of life. But when the hatch opens and Nora steps out, she is not 65. She is not even 40. She is 29. Because for her, on the ship, at Gamma 10, time has run 10 times slower. 40 years on Earth has translated to 4 years of ship time. She left at 25. She has aged 4 years. She comes back at 29. Stop and picture this. Stop and really see it. Two women who were born on the same day, same hour, same minute, meet each other on a landing pad. One is old, one is young, same genes, same memories of a shared childhood. But one of them has lived through 4 decades of history, through wars and elections and technological revolutions and the deaths of their parents and the births of grandchildren. And the other has been in a ship for 4 years, reading, sleeping, eating, watching the universe bend past her windows. They hug, and in that embrace is the strangest fact in all of physics, the asymmetry of time itself. The loss of shared chronology between 2 lives that started identical. This is not metaphor. This is the real, tested, physically measured consequence of relativity. Now, I know the word paradox is in the name of this thought experiment, and some people will ask, but wait, from Nora's perspective on the ship, is not Anya the one who is moving, since motion is relative? And does not that mean that from Nora's perspective, Anya should be the one aging slowly? Why does it come out asymmetric? This is a legitimate question, and the answer is that the 2 situations are not actually symmetric. Anya stays in the same inertial reference frame the entire time. Nora does not. In order to come back, Nora has to decelerate, turn around, and accelerate in the opposite direction. That period of acceleration breaks the symmetry between the 2 perspectives. From a technical standpoint, the acceleration phase is what makes Nora's frame non-inertial, and general relativity tells us that time runs differently in accelerated frames. When you work through the full math, including the acceleration, you find that only one of them, the one who turned around, ends up younger. The stay-at-home twin is older. There is no actual paradox. There is only counterintuitive math that resolves cleanly when you include all the physics. And, lest anyone think this is purely theoretical, let me walk you through the experimental evidence, because this is not speculation, this is measured. In 1971, 2 physicists named Joseph Hafele and Richard Keating put cesium atomic clocks on commercial jet airliners and flew them around the world in opposite directions, once eastward, once westward. When they compared the flying clocks to stationary clocks left on the ground at the US Naval Observatory, the flying clocks had accumulated different amounts of time, exactly matching the predictions of relativity to within experimental error. The differences were tiny, a few 100 billionths of a second, because the speeds were small compared to light, but they were measurable, and they were exactly what Einstein's equations predicted. Time dilation is not a thought experiment. It is a phenomenon. Even more dramatically, the entire GPS system that lives in your phone would not work without relativistic corrections. The GPS satellites orbiting Earth are moving at about 14,000 kilometers per hour relative to the ground, which causes their onboard clocks to tick slightly slower than ground clocks due to special relativity. At the same time, they are farther from Earth's gravitational field, which, due to general relativity, causes their clocks to tick slightly faster. The 2 effects partially cancel, but not completely, and the net result is that GPS satellite clocks gain about 38 microseconds per day relative to ground clocks. That sounds tiny, but over a day, uncorrected, it would cause GPS location errors of about 10 kilometers. Your Maps app would think you were 10 kilometers off. The engineers who designed GPS had to build in relativistic corrections just to make the system work. Every single time you pull up directions on your phone, Einstein's equations are running in the background, invisibly correcting for time dilation. Relativity is not a curiosity, it is load-bearing infrastructure. Another case. Muons are tiny subatomic particles that are produced when cosmic rays hit Earth's upper atmosphere. They have an average lifetime in the lab of about 2.2 microseconds before they decay into other particles. At that lifetime, moving at almost the speed of light, they should only be able to travel about 600 meters before decaying. But we detect muons at sea level, hundreds of meters below where they were created, in numbers that should be impossible if they only lived 2.2 microseconds. The reason they make it down is time dilation. From our perspective on the ground, the muon's internal clocks are running slow because they are moving so fast. Their effective lifetime is stretched, and they travel much farther than classical physics would predict. This effect is observed every single day in physics labs around the world. It is as close to a routine experimental confirmation of relativity as you can get. So the twin paradox is not paradoxical, and it is not abstract. It is what will happen, physically really, to any astronaut who undertakes a relativistic journey. They will age less than the people they leave behind, and the faster their ship goes, the bigger the gap. At low velocities, it is a few microseconds. At Nora's gamma of 10, it is 36 years of lost shared time. At a gamma of 100, pushing for the galactic center, the crew of a relativistic ship could come home to an Earth that had experienced tens of thousands of years of history. 39 years of ship time for the trip, and 39 more to come back, and in that time, Earth ages 50,000 years, or 100,000, or 200,000, depending on the exact profile. Entire civilizations would rise and fall in the window while the crew was in transit. Languages spoken when they left would be lost or unrecognizable upon return. The continents themselves would not have meaningfully moved, but everything built on top of them would have transformed beyond all recognition. And here is the haunting part. If the traveller went to Andromeda and came back at a gamma of 50,000, the round trip would take roughly 5 million years of Earth time. 5 million. There would be no Earth to return to in any recognizable sense. Humanity would be gone, or evolved into something unrecognizable, or spread across the stars, or extinct. The planet would still be there, the sun would still be there, but the world, the civilization, the home would be gone. Every person the traveller ever knew would be a fossil, a name on a crumbling document, or less. The relativistic traveller does not just journey through space. They journey in a one-way direction into the deep future of the universe. The door opens, but it only opens one way. And this, more than any energy cost, is the central cost of the loophole. It is the price that no engineering can ever reduce. It is the price of exile. Part 13. The Energy Catastrophe. Before we get too swept up in the philosophical weight of what relativistic travel would cost us emotionally, let me bring you back down to the hard reality of physics. Because there is another price, and this one is counted in joules. Because achieving these relativistic velocities is not just difficult, it is staggeringly, civilization-breakingly difficult. It is the kind of difficult that would require humanity to harness forms of energy we do not yet know how to access. Remember the central thread we keep returning to. Velocity determines how much of the universe you can cross in a lifetime. And velocity, at relativistic scales, requires energy that scales in a brutal, non-linear way. Newton's classical equation for kinetic energy, the energy of motion, says that it equals 1/2 the mass times the velocity squared. That is the equation most of us learned in school. Under that rule, doubling the velocity quadruples the energy. Tripling the velocity increases the energy 9-fold. Bad, but manageable. Relativity rewrites this equation. The relativistic kinetic energy equation, without showing you the formula, has a crucial feature. As velocity approaches the speed of light, the energy required does not just grow as the square of velocity, it goes toward infinity. The curve bends upward, harder, and asymptotes at the speed of light itself, which is why nothing with mass can ever actually reach the speed of light. The closer you get, the more energy each additional increment costs, until the energy required to reach the speed of light is literally infinite. Let me put numbers on this. To accelerate a spaceship with a mass of 1,000 metric tons, which is about the mass of a modern cargo ship, to 90% of the speed of light, you would need approximately 10 to the 23rd joules of energy. That is 10 followed by 23 zeros. To give you a sense of scale, the total energy consumption of the entire human species in a year is around 6 times 10 to the 20th joules. So accelerating our little 1,000-ton ship to 90% of light speed would require about 160 years of the entire world's current energy output, and that is just to accelerate. You would need the same again to decelerate at the destination, and the same again to come back, and the same again to stop at Earth, 4 times minimum. And you need that ship to be carrying its own energy source, so the fuel itself has mass, which means you need more energy to push the fuel, which is the rocket equation problem we talked about earlier, reasserting itself with a vengeance. Now pushed to 99.9%, gamma of 22. The energy required is not just a bit more, it is about 22 times more. And at 99.9999%, gamma 500, it is 500 times more. The numbers very quickly become ridiculous. To send a human to Andromeda and back at the gammas needed, you would need energy levels equivalent to the total output of the Sun for thousands of years, captured and directed into a single spacecraft. This is not an engineering problem that will be solved by better batteries. This is an energy source problem. We need fuels or methods that release thousands or millions of times more energy per kilogram than anything we currently use. The most efficient chemical reaction releases about 3 times 10 to the 6th joules per kilogram of fuel. Nuclear fission releases about 10 to the 14th joules per kilogram, roughly 100 million times more. Nuclear fusion can do slightly better. And then there is antimatter. When antimatter meets ordinary matter, they annihilate completely, converting all of their mass into energy, according to Einstein's famous E equals mc squared. The energy released per kilogram is about 9 times 10 to the 16th joules. That is 100 billion times more than chemistry, about 1,000 times more than fission. Antimatter is, in a very real sense, the maximum possible fuel. There is no more efficient way to release energy from matter that we know of. So why are we not already building antimatter starships? Because producing and storing antimatter is the hardest thing humanity has ever tried to do at scale, and we are very bad at it. Right now, humanity produces antimatter in tiny quantities at particle accelerators like CERN in Switzerland and Fermilab in the United States. The total amount of antimatter ever produced by the human species, from all sources, is about 20 nanograms. 20 nanograms, not 20 grams, not 20 micrograms, nanograms. A single grain of sand weighs about 50 million nanograms. We have produced less antimatter in total over the entire history of the field than is contained in a grain of sand. And the cost, because of the staggering energy inefficiency of our production methods, works out to something like $60 trillion per gram. And then there is storage. Antimatter cannot touch ordinary matter because when it does, it instantly annihilates, converting its mass into pure energy and releasing an intense burst of gamma radiation. To store it, you have to suspend it in a vacuum using magnetic or electric fields, holding it away from all surfaces. Current state-of-the-art storage can keep small quantities of antimatter for a few minutes to a few hours before containment fails. Storing enough antimatter to fuel a relativistic starship for the years of travel required is a technology we do not possess and may never possess with current approaches. So even if antimatter is the theoretical ideal fuel, we are about as far from using it practically as the ancient Egyptians were from building a jet airplane. Meanwhile, fusion, the middle ground between chemistry and antimatter, keeps being promised as just decades away. And to be fair, enormous progress has been made in the last few years, with facilities like the National Ignition Facility in California achieving net energy gain from controlled fusion reactions for the first time in 2022. But controlled, continuous fusion at the scale needed for propulsion is still a long way off, and even fusion, for all its promise, falls short by orders of magnitude compared to what relativistic travel would require. Fusion might get us to a few percent of light speed. That would open the nearest stars. It would not, by itself, open the galaxy. So this connects us back to our central thread with brutal clarity. The door exists. The loophole is real. The math of relativity allows a single human to traverse the universe within their lifetime. But the amount of energy required to open that door, even a crack, is beyond anything our species currently has access to. It may remain beyond us for a very long time, possibly forever, unless we figure out energy extraction methods we cannot yet imagine. Velocity determines reachable distance. Energy determines velocity. And the energy curve, like everything else in this story, goes to infinity as you approach the speed of light. The cost of crossing more of the universe scales against you the harder you push. And for a human-scale mission, the cost is immense, even at relativistic speeds that are technically permitted by physics. The wall is real, the door is real, but the door is very, very expensive to open. And the expense is written into the same equations that tell us the door is there. Part 14. What the universe looks like at 99% of light speed. Let me briefly take you inside the ship, because I think you should know what it would actually look like out the window if you were on a journey at 99% of the speed of light. Because relativity does not just compress time and distance, it also completely distorts what you see. The universe, through the windows of a relativistic ship, is not the universe you know. First, there is an effect called relativistic aberration. As you approach the speed of light, the light from stars around you gets compressed into a narrow cone in front of you. Stars that are actually off to your sides, or even behind you at rest, appear to be bunched up ahead of you in a kind of bright tunnel. The stars behind you fade into darkness. The rear view is black. The forward view is a dazzling, compressed cluster of light. You feel, visually, as though you are flying into a bright circle with darkness all around you. The geometry of your vision has been warped by the math of your motion. Second, there is Doppler shifting. As you approach the speed of light, the wavelengths of light coming from objects ahead of you get compressed, shifting them to shorter wavelengths. Ordinary starlight, which looks yellow or white, shifts first to blue, then to ultraviolet, then to X-rays, and at extreme velocities, all the way to gamma rays. Meanwhile, the few photons that do reach you from behind are stretched to longer wavelengths, shifting from visible light down through infrared to microwaves and radio. The universe, in your reference frame, has been wrenched across the electromagnetic spectrum. What you perceive as visible light from the cone of stars ahead is actually light that started out as radio waves, stretched through the journey into your eyes. And what used to be visible light is now invisible X-rays that would pass through your body. Third, there is the problem of the interstellar medium itself. Interstellar space is not empty. It is filled with a thin gas of hydrogen atoms, about 1 atom per cubic centimeter. At ordinary speeds, this gas is irrelevant. At 99.9% of light speed, each of those hydrogen atoms hits the front of your ship with the energy of a high-speed particle accelerator collision. A single gram of ordinary air encountered at relativistic velocity would deliver the energy of a massive bomb. The ship, flying through the interstellar medium at these speeds, is essentially ploughing through a continuous, intense stream of radiation. Shielding requirements would be extraordinary. You would need meters of dense material on the front of the ship just to absorb the incoming particles, and the shielding itself would heat up, glow, and need to be actively cooled. Put all of this together, and what you get is a journey in which the universe outside your windows is not familiar. The sky compresses into a bright cone ahead. The stars glow in colors your eyes were never meant to see. The front of your ship blazes with the heat of constant bombardment. Behind you, darkness. Inside, you and your crew, experiencing normal gravity from the 1G acceleration, living out years that correspond to centuries back home. And connecting all of this back to our central thread Even the visual experience of relativistic travel reinforces the fundamental lesson. Crossing real cosmic distances within a lifetime does not just require extreme velocity and extreme energy. It requires you to enter a mode of existence in which the universe itself looks and behaves differently from anything human eyes have ever seen. The door to the cosmos is not only expensive, it is also a door into strangeness. Part 15. The final barrier, the universe itself. Just when you think the story has reached its most constrained point, physics reaches in and hands us one more limitation, one more hard ceiling on how much of the universe a human could ever, even in principle, cross. And this one is maybe the strangest of all, because this one is not about our technology, or our fuel, or our biology. This one is about the fact that the universe itself is not sitting still, it is expanding. And the farther away things are, the faster they are moving away from us. And that expansion defines a boundary, a kind of cosmic horizon, beyond which no matter how fast we travel, we can never reach. When astronomers in the early 20th century, particularly Edwin Hubble in the 1920s, began measuring the distances to other galaxies, they noticed something strange. Almost every galaxy they measured was moving away from us. And the farther away a galaxy was, the faster it was moving. This was not because Earth was in a special central location. It was because the whole fabric of space itself was expanding. Every galaxy was moving away from every other galaxy, like raisins in a rising loaf of bread. This discovery led to the Big Bang theory and to our modern understanding of cosmology. And then, in 1998, two independent teams of astronomers made a discovery that won them the Nobel Prize. They found that the expansion of the universe is not slowing down, as you might expect from gravity pulling things together. It is accelerating. Some mysterious force, which we have labeled dark energy without really understanding what it is pushing the universe apart faster and faster. The consequence of accelerating expansion for our story is profound. It means that the reachable universe, even in principle, is bounded, and that boundary is shrinking over time. Let me unpack this. The observable universe is about 93 billion light-years across in diameter, which sounds enormous. But the observable universe includes regions we can see, because their light, traveling for billions of years, has reached us. It does not follow that we could reach them. And in fact, most of what we can see is already beyond our ability to ever contact, because by the time a signal or a spacecraft from us reached those distant regions, the expansion of space would have carried them even farther away. There is a horizon called the cosmological event horizon, which currently sits at a distance of about 16 billion light-years. Any galaxy beyond that horizon is permanently unreachable. No matter how fast we travel, no matter how much energy we have, no matter what technology we develop, we cannot catch up to it. The expansion of the universe is carrying it away faster than any signal we could send. And here is the heartbreaking part. As time passes, the cosmological event horizon moves inward. Regions of the universe that are currently inside our horizon, meaning they are, in theory, reachable, are gradually crossing out of it. In about 100 billion years, if current trends continue, almost all of the galaxies we can currently see will have receded beyond our event horizon. Our descendants, if any exist that far in the future, will look up at a sky that contains only our own Milky Way and a few nearby galaxies, the members of what astronomers call the local group. Everything else will have faded out of sight, carried beyond reach by the relentless acceleration of space itself. The universe is not just too big to cross. It is actively shrinking, in terms of what is reachable, with every passing moment. Now, connect this back to our central thread. We started with the question of how much of the universe a human could cross in one lifetime. We worked out, through relativity, that in principle, the entire observable universe becomes accessible to a sufficiently fast traveler within their own subjective time. But that was assuming a static universe. Factoring in cosmological expansion, the answer changes. There is a maximum reachable volume defined by the event horizon, and it is smaller than the observable universe, and it is getting smaller. Every year, galaxies slip out of reach. Every 1,000 years, more. The deadline for visiting any given distant galaxy is real, and eventually it expires. If humanity wanted to reach, say, a galaxy currently 15 billion light-years away, we have maybe a finite window in which to do it. After that, no matter how advanced we become, no matter how relativistic our ships, that galaxy is lost to us forever. This is the third wall. The first was the walls inside our own physics, the rocket equation and the energy catastrophe, which constrain how fast we can go. The second was the subjective cost of time dilation, which separates the traveler from everyone they leave behind. And the third, the one we just added, is cosmological. The universe itself is running away from us. Even if we somehow developed perfect relativistic travel and effectively infinite energy, we would still not be able to reach all of it. Part of the universe is already out of our grasp, and more of it leaves our grasp every day. There is a cosmic deadline written into the expansion of space, and that deadline is a reminder that our window, as a species, is finite. The door exists, the loophole works, but the door is closing. Part 16. The one-way geometry of reality. Let me now tie every thread of this story together, because we have covered a lot of ground, and the conclusions are worth seeing in one sustained breath. We started with the idea that the limit on how much of the universe a human could cross in a lifetime seemed, at first glance, to be about distance. Space is huge. We are small. Our machines are slow. How could anyone cross cosmic distances in 80 short years? And then, piece by piece, we learned that distance is not really the limit. Velocity is. And velocity is constrained by energy, which is constrained by the mathematics of propulsion and the fundamental properties of the fuels available to us. And these constraints, chained together, seem to close the door entirely. But relativity, through Einstein's work in 1905, showed us that there is a loophole. Time dilation and length contraction mean that a sufficiently fast traveller can, in their own subjective time, cross arbitrarily large distances. The ship's clock ticks slowly. The journey compresses. A 20 light-year trip becomes a year of ship time at high gamma. A 2.5 million light-year trip becomes 30 years at extreme gamma. In principle, the entire observable universe becomes traversable within a single human life. That is an almost incomprehensible inversion of the problem we started with. The door is there. It opens. Physics itself lets us in. But the door has a shape. It is not a door you can walk through in both directions equally. It is a door with a specific one-way geometry, and that geometry is the haunting punchline of this whole story. Because while the traveller on the ship is experiencing compressed subjective time, the universe outside is not. Earth is still ticking along at its normal pace. The solar system is still orbiting the galactic centre at its usual rate. The galaxies are still drifting apart at their usual speeds. All of that continues while the traveller is compressed inside their relativistic bubble. And when the traveller arrives at their destination, or comes back, they find that everything has moved on. Let me make this concrete one more time. Say a crew of 5 leaves Earth for Andromeda. Their ship accelerates at 1G for most of the trip, reaches a peak gamma around 50,000, and arrives at Andromeda after 30 years of ship time. Wonderful. Historic. They are the first humans to have left the Milky Way entirely. They step out into a completely different galaxy. They look back and can see the entire Milky Way as a glowing spiral in their rear view, a full galaxy seen from outside, something no human has ever witnessed. It is the single greatest view in human history. And behind them, back on Earth, 2.5 million years have passed. 2.5 million. Homo sapiens, the species that launched them, has almost certainly either gone extinct or evolved into something unrecognizable. The civilization that built the ship is dust, 50,000 times over. The languages spoken at launch are lost. The names of the people they loved are not even footnotes in any surviving record. There is, in any meaningful sense, no home to return to. And if they did return, the round trip would add another 2.5 million years to the Earth clock, for a total of 5 million years in the rear view. 5 million years is longer than the entire history of our genus. This is the cost. This is the haunting asymmetry. The door to the universe opens, but walking through it is a permanent severance from everything you have ever known. The traveler does not just travel in space. They travel irrevocably forward through time. There is no coming back in any meaningful way. Relatives are gone. History is unrecognizable. The civilization you launched from no longer exists in any form you would recognize. You have, in effect, immigrated to the deep future of the universe, and that is not a scenic detour. That is not a 2-week vacation. That is the conditions on your ticket. There is no round trip. There is no return to origin. Every relativistic journey of significant gamma is, in effect, a one-way journey into a future that does not contain the world you left. Einstein himself, later in his life, described time as what he called a persistent illusion. He wrote in a letter to the family of a dear friend who had died that, for those of us who believe in physics, the distinction between past, present, and future is an illusion, however persistent. What he meant was that, in the mathematical structure of relativity, all events in space-time are, in some sense, already there. Past and future are not fundamentally different from each other. They are just different coordinates on the same 4-dimensional fabric. The reason we feel time flowing forward is a feature of our biology and consciousness, not a fundamental property of the universe. And yet, when we try to apply this mathematical insight to the question of travel, we find that we cannot undo the forward motion. A traveler who compresses their own time by moving fast still emerges at the other end into the future of the universe. The illusion persists, but it still carries us forward. And then there is the cosmological layer. Not only is the traveler cut off from their own origin civilization, but the universe itself is shrinking in terms of what remains reachable. As time passes, more galaxies slip beyond the cosmological event horizon. If the traveler could, somehow, live long enough to attempt a second journey, their options would be fewer. The universe closes, slowly, over eons, until eventually, even from the Milky Way, only the nearest galaxies remain visible, and the rest of the cosmos is gone forever. There is a cosmic deadline. There is a window of opportunity. And while it is vast by human standards, it is finite. So we arrive, finally, at the reframed question. The question we started with was, how much of the universe could a human actually cross in a single lifetime? And the answer, if we are being rigorous, has 3 layers. At current technology, the answer is essentially 0. A tiny smudge not much beyond the Oort cloud. At hypothetical relativistic technology, operating within the laws of physics but requiring impossible amounts of energy, the answer becomes, in principle, the entire observable universe. A person could cross galaxies, even intergalactic voids, within their own subjective life, but that answer comes with the permanent forfeit of everything you leave behind. And overlaid on top of both of those, the cosmological horizon sets an outer boundary, beyond which even perfect relativistic travel cannot reach, and that boundary is shrinking. So the final question is not really, how far can you go? It is not even really, how much energy would you need, though the energy is staggering. The final question, the one that this whole conversation has been building toward, is a philosophical one. Would you go? If the door existed, if tomorrow someone built a ship that could take you to Andromeda in 30 years of ship time, knowing that you would return, if you returned at all, to an Earth 5 million years older than the one you left, where no human you have ever loved is still alive, where your own species has given way to something or nothing, would you walk through the door? What would you need to believe, to leave, with full knowledge that what you are doing is not travel, but exile? What would you be trying to see? What would you hope to learn? What would it be worth? And this is the shape of the answer that physics has given us. The universe is not closed to humans. We were told, for a long time, by the arithmetic of distances, that we were permanently quarantined on our little planet, that the stars were decoration, that the rest of the cosmos was as unreachable as an afterlife. That was wrong. The universe is open, in principle, to anyone who can cross the threshold of enough velocity. But the threshold is high, the cost is civilizational, and the price of admission is everything you leave behind. The loophole is real, the door is real. The door opens, but every step through it is a step away from the world you came from, and the world behind you ages faster than you can turn to look at it. Every mile of distance gained is a decade of time lost to the people you left. Every galaxy reached is a civilization unrecognizable in the rear view. So the answer to our original question is, honestly, both at the same time. In principle, a human could cross the entire observable universe in a single lifetime. In practice, with the energy and technology we currently possess, we cannot leave our own cosmic neighborhood. And even if we solved the energy problem, even if we built the perfect ship, the journey itself would be a kind of chosen solitude, a willing departure from the home we came from. Not because space is empty, but because time will not wait for us while we cross it. The same physics that gives us the door takes away the road back. Physics allows intergalactic travel within a lifetime. Energy makes it nearly unattainable. Time makes it irreversible. And the universe itself, through its accelerating expansion, is shrinking the window in which any of this would be possible. These four facts, braided together, form the honest answer to the question. Not 1/80th of a light year, which is what current technology offers. Not the entire cosmos, which is what naive relativity promises, but somewhere between, a sliver of the universe that becomes, for the right traveller, reachable, a sliver that costs everything to reach. The limit is not distance. The limit is not even energy, though energy is the gatekeeper. The limit is what you are willing to lose, because the farther you go, the less of your world still exists when you arrive, and the universe, for all its majesty, does not wait for you. It never has. It moves forward, expanding, drifting apart, whether or not any eyes are left to watch it. The question of whether any of us, as a species, will ever actually step through that door is one that humanity has not yet answered. Maybe we never will. Maybe one day, a small group of people will stand on a launch pad saying their final goodbyes, knowing that when they return, if they return, Earth will be older than all of recorded history, stacked upon itself thousands of times over. Maybe they will go anyway, because something in the human mind cannot stop asking what is out there. Maybe the universe is best visited, in the end, by those willing to lose everything else to see it. And maybe, for now, all we can do is look up at the cold, bright sky, at the galaxies drifting farther away from us every second, at the cosmos that is, technically, within reach, and yet somehow just out of reach, and ask, quietly, the way Einstein asked, the way all of us ask when we are honest about it, how much of this were we ever really meant to see? How much of it were we ever really meant to hold? Because the door is open, the universe is out there, but every journey through it is a goodbye, and the farther you go, the more of your world is gone by the time you arrive. That is the geometry, that is the price, That is the deal the universe is offering. And it is up to us, as a species, to decide whether we are ever truly going to take it.